The toxicity of seed oils has been gaining traction in the health world. But besides avoiding them, what can we do to protect ourselves from their negative health effects? In this video, I'm going to summarize some of the core issues with seed oils and provide you with 3 key solutions that I've used with myself and with my clients to protect against these negative effects of seed oils. So in order to understand why I am recommending these 3 key solutions for managing seed oils, I first want to talk about what some of these major problems are with seed oils. And one of the big components is that they are high in omega-6 polyunsaturated fatty acids. So I have 4 of the major seed oils picked out here. We have soybean oil, corn oil, sunflower oil, and canola oil. And I've set them all to 100 grams so we could see what percentage omega-6 polyunsaturated fatty acids that they have, or polyunsaturated fatty acids in general. So soybean oil is 50.9 grams of omega-6, which make about 51% omega-6. And it has about 6.6 grams of omega-3. This is not long-chain omega-3s. This is things like alpha-linolenic acid. Next, we have corn oil. The corn oil is at 51.9 grams of omega-6 polyunsaturated fatty acids with about 1 gram of omega-3. Again, not a long-chain EPA or DHA that's found typically in fish. Sunflower oil, we have 65.7 grams of omega-6 polyunsaturated fatty acids and no omega-3s listed. And the last one is canola oil. Canola oil is about 17.8 grams of omega-6 and 7.5 grams of omega-3, which is alpha-linolenic acid, which again is not the long-chain DHA, EPA that we see from fish. And we'll talk about that in just a little bit, so stay tuned on why I'm bringing that up. But essentially what we're seeing is the major seed oils that we see in the diet are quite high in omega-6 polyunsaturated fatty acids, much more so if you put chocolate, roughly 100 grams of chocolate, you have only 3 grams, so 3% omega-6 polyunsaturated fatty acids with about 0.1 omega-3 polyunsaturated fatty acids. The omega-6 polyunsaturated fatty acids and the polyunsaturated fatty acids in general were considered to be, or are considered to be, essential fatty acids. This was from the work of the Burrs, but the requirement is actually exceptionally low. Some of the newer research actually calls this into question, but essentially what the researchers say here from linoleic acid and regulation of glucose homeostasis, they say, while a daily intake of linoleic acid around 1 to 2% of total calories is sufficient to prevent the development of essential fatty acid deficiency, the over 10-fold increase in linoleic acid consumption since the mid-20th century has prompted further research as to how linoleic acid can impact long-term health. So even with that, 1 to 2%, it's exceptionally low, but there's actually quite a few pretty solid arguments that it is even lower than that, up to about 0.5%. But let's just run with 2%. So they're saying that there's a requirement for these fats around 1 to 2% of calories. Now, the next thing is the consumption of omega-6 polyunsaturated fatty acids, despite the requirement only being 1 to 2% of calories, has exploded from seed oils since 1909. So we have a graphic here. And what we could see is that from 1909 to 1999, soybean oil and canola oil have gone out of control. These have been 2 of the biggest seed oils. And the soybean oil has started to pick up since about 1950s, 1960s. And then the canola oil actually started to pick up around the 1990s or so. Their intake has drastically increased. And with the increase in this intake, the amount of linoleic acid, which is the omega-6 polyunsaturated fatty acid, has drastically increased as well as a percent of energy in the diet. So in 1909, about 2% of people's calories were coming from linoleic acid. And in 1999, it's about 8%, and now it's even higher. So this has drastically increased over time. We have a very low requirement for polyunsaturated fatty acids, 1 to 2% of calories, and even then, that's probably higher than is what's actually true, particularly for the omega-6. But there's some problems with these fats. They are extremely likely to be damaged by oxidative stress. They can be peroxidized very easily because of their double bond structure. A table here that shows us how likely they are to be damaged. We see saturated fats and monounsaturated fats, basically zero. Like their ability to be damaged is very, very low. But when we get to polyunsaturated fats, we have omega-6 polyunsaturated fats. When you look at linoleic acid, it's significantly higher, many times higher than saturated and monounsaturated fats. I know the scale is 2, 4, 6, 8, 10. And then over here, we have arachidonic acid, which is significantly different even to linoleic acid. And we get to the omega-3 polyunsaturated fats. They're even worse than the omega-6 in terms of their susceptibility to oxidative stress. So we have alpha-linolenic acid here. And then we have DHA here, which is significantly more likely to be damaged than arachidonic acid and linoleic acid and also alpha-linolenic acid. This is basically the more double bonds these fats have, the worse their susceptibility is to actually being damaged. So we have these highly peroxidizable fats, with a very low requirement from them being massively exploded in the diet. Next up, we have the omega-6 polyunsaturated fatty acids. Despite being less likely to be damaged, are actually the primary precursors to the inflammatory mediators in the body called the eicosanoids. So we have a graphic here, and what we can see is that omega-6 fatty acids, this is linoleic acid as an example, but you also have arachidonic acid, can be converted to arachidonic acid in multiple steps, and then that can get converted into these inflammatory mediators through the enzymes lipoxygenase, cyclooxygenase, and cytochrome P450 enzymes. And they create a variety of different inflammatory mediators here. You can see them listed here. I'm basically laying the groundwork for what strategies we're going to use to protect ourselves from these fats by showing you what the actual problems are, or some of the problems. Just to show this here, that linoleic acid, they still see in studies that you see increases in these inflammatory mediators with the linoleic acid intake. So the researchers here from a paper titled Linoleic Acid and the Regulation of Glucose Homeostasis, or a review of the evidence, say, while relatively little linoleic acid is metabolized to arachidonic acid, several studies have found that diets rich in linoleic acid can still significantly raise plasma arachidonic acid-derived bioactive lipids, which is important as the arachidonic acid serves as the parent molecule for all inflammatory eicosanoids. Even though the conversion between linoleic acid and arachidonic acid, it's not massive, when you increase a linoleic acid content in the diet, you still see an increase in these inflammatory mediators. The next thing is there are other components called oxidized linoleic acid metabolites, and linoleic acid directly increase the production of these, and they are strongly associated with a variety of pathological conditions. The paper titled here is Lowering Dietary Linoleic Acid Reduces Bioactive Oxidized Linoleic Acid Metabolites in Humans. And the researchers say oxidized linoleic acid metabolites, abbreviated OXLAMs, are pleiotropic bioactive derivatives of linoleic acid. And so we have a graphic here to show you. So you have linoleic acid, the omega-6 polyunsaturated fat. That's what we were seeing with the seed oils I showed you in Chronometer. And they can convert linoleic acid to these mediators, or they can actually spontaneously, through non-enzymatic action, get converted into these different mediators that we see here. So that leads me to the next thing. These polyunsaturated fatty acids are directly involved in a variety of pathologic conditions, including Alzheimer's and dementia, cardiovascular disease, fatty liver, etc. And so we have a quote here from a paper titled Lowering Dietary Linoleic Acid Reduces Bioactive Oxidized Linoleic Acid Metabolites in Humans. And they say, as a major component of oxidized low-density lipoprotein and atherosclerotic plaques, oxidized linoleic acid metabolites are reported to play a central role in foam cell formation and the pathogenesis of atherosclerosis. These metabolites are involved directly in atherosclerosis. Oxidized linoleic acid metabolites also can act as endogenous TRPV1 receptor channel activators, facilitating peripheral and central pain sensitization. So they are involved in increasing the sensitivity to pain. Then you see here circulating oxidized linoleic acid metabolites, which are elevated in Alzheimer's, dementia, and non-alcoholic steatohepatitis, which is essentially fatty liver disease, have been proposed as a mechanism-based biomarker useful for indicating the presence and severity of both conditions. They're talking about gauging whether these conditions are present as well as how severe they are just based on these factors alone. What I want to get to is the strategies. These strategies I'm about to discuss are strategies that I've used myself and also strategies that I've used with my clients to help improve cardiovascular risk factors and markers in their labs, as well as liver function markers, and then also body composition, just by adjusting these different components. So strategy number one to manage the polyunsaturated fatty acids, particularly omega-6 fatty acids in the diet, is to keep the total omega-6 content around 2% of calories or less, which is actually quite difficult to do because it's present in almost all the foods. Essentially, that works out to be about 4 grams of omega-6 polyunsaturated fatty acids per 2,000 calories. And this is a target that has been directly mentioned by Dr. Rapey multiple times, but essentially this would be the target to set. And again, this is the absolute minimum threshold. It is actually lower than 2%. So we want to just at least try to get 2%. And it's not that you can't try to go lower. It's just that it gets really hard. So in order to do this, the best way is to shift the fat sources in your diet to be composed of things like olive oil, avocados, macadamia nuts, cocoa butter, dark chocolate, coconut and coconut oil, beef fat, egg yolks that are pasture raised, and then dairy fats if tolerated. These are going to help you get closer to that target than if you were to incorporate large amount of seed oils, soybean oil, corn oil, sunflower oil, etc. in the diet. It's going to be extremely difficult to actually keep the omega-6 polyunsaturated fat at that target to keep the total levels low. So you want to shift these other fat sources. Now, I do have a free video series and PDF guide that shows you how to construct your diet using these fat sources. It's called the Nutrition Blueprint. So I'll drop a link in the description. You can check that out. Once you keep your total omega-6 polyunsaturated fat intake quite low, the next question that I always get from clients is, what do I do with my omega-3s? Mike, what do you think about omega-3s? There are some problems with omega-3s, and we're going to talk about them. But what I want to mention here is there is some research talking about ratios of omega-3s. In the research, what they tend to find is that ratios, even at 6-to-1 down to 3-to-1 of omega-6 to omega-3, they see benefits and they see associations. So I want to talk about some of these studies. We have a paper here titled Linoleic Acid and the Regulation of Glucose Homeostasis, our view of the evidence. And what they say is, historically, the ratio of dietary omega-6 to omega-3 PUFA has been used as an indicator to measure risk associated with development of some chronic metabolic disorders. A greater omega-6 content in ratio to omega-3 has generally corresponded with the stimulation of inflammatory pathways that are prothrombotic and pro-aggregatory, while lower omega-6 to omega-3 ratio is thought to lead to the dominance of anti-inflammatory resolvins, protectins, and marasins. Evolutionary studies have estimated that the omega-6 to omega-3 ratio of the human diet was historically 1-to-1, but advocacy efforts throughout the 20th century by health agencies to increase omega-6 polyunsaturated fat consumption have resulted in an increase in modern Western diet of omega-6 to omega-3 to an average of 10-to-1. It used to be 1-to-1 is what they're saying in this paper, and now it's around 10-to-1. And what they're going to talk about here are some better ratios. So what they say here is several reviews have proposed reducing the omega-6 to omega-3 ratio as a primary preventative measure to protect against various cancers, cardiovascular disease, type 2 diabetes, obesity, as well as other chronic metabolic disorders. In general, the studies referenced by these reviews have provided promising data on a variety of benefits associated with a lower omega-6 to omega-3 ratio, but it is clear additional research is needed. For example, studies from India evaluating the effects of diets with a different omega-6 to omega-3 ratio on insulin action found that a lower omega-6 to omega-3 ratio could reduce, so that was at a 6-to-1 ratio, could reduce the prevalence of type 2 diabetes. And then they say, similarly, the Lion-Heart study, which compared a Cretan Mediterranean diet with a 4-to-1 ratio to the Step 1 American Heart Association diet, found that a lower omega-6 to omega-3 ratio diet led to a 70% decrease in total mortality. So even going 10-to-1 to 4-to-1 led to a significant decrease in overall mortality. What's the takeaway from this for me? Well, if we have 4 grams per 2,000 calories and we look at maybe a 4-to-1 ratio of omega-6 to omega-3, you're looking at maybe around a gram or less of omega-3 per day. And ideally, that would be coming from eating adequate seafood in the diet. So my recommendation isn't even to try to massively intake omega-3s, just incorporate seafood in the diet. So that's going to be cod, that's going to be sole, flounder, shrimp, scallops, mussels, oysters, clams. And then periodically you could have some tuna, it's just higher in mercury. Sardines, you could have salmon, except that high amounts of those are going to give you very high intakes of omega-3s, which can be quite problematic. With that in mind, we have a paper here titled Linoleic Acid and the Regulation of Glucose Homeostasis, a review of the evidence. And the authors say here, studies that have reported the overconsumption of omega-3 PUFAs indicate both potential deleterious and beneficial effects, such as increased serum glucose, significantly decreased coagulation, and reduced blood pressure. Taken together, it is possible that the consumption of specific dietary PUFA species may indeed be governed by the Goldilocks principle, whereby moderation of omega-6 PUFA or polyunsaturated fats and omega-3 polyunsaturated fat intake produce optimal metabolic effects. So it's not about massively increasing omega-3. It's about lowering total omega-6 and just having an adequate amount of omega-3 in the diet, ideally from seafood sources. Because again, keep in mind, omega-3s are even more susceptible to oxidation than the omega-6s are. The next thing is, if you've been eating seed oils for a long time and you're loaded up on polyunsaturated fats, these next 2 strategies are going to be quite important for you. The first thing is, there's a variety of antioxidant compounds that you can stack together to protect yourself from the lipid peroxidation that occurs with the polyunsaturated fats. So the first one is vitamin E. Vitamin E is one of the major lipid-soluble antioxidants, and it's been known to actually protect against lipid peroxidation. And so I have a quote here. It's lipid oxidation that is and is not inhibited by vitamin E. And they say it has been established that vitamin E acts as an essential peroxyl radical scavenging antioxidant to inhibit free radical mediated lipid peroxidation. So it basically blocks lipid peroxidation. Vitamin E scavenges lipid peroxyl radicals before they attack substrate lipid molecules, including fatty acids, phospholipids, acylglycerols, cholesterol, and cholesterol esters. So the vitamin E can protect against the different fat components of our bodies from being damaged by lipid oxidation. And we have a graphic here that shows this. So you have a lipid peroxyl radical. It interacts with vitamin E. You get a lipid hydroperoxide, which basically nullifies this product here. It's still not great, but at the same time, it's not going to keep driving the lipid peroxidation. And then the vitamin E gets recycled by the vitamin C. This is how vitamin E is protecting against lipid peroxidation. Now, as we can see, vitamin E doesn't work alone and works with vitamin C. And so we have a clinical trial here. This is actually a double-blind, placebo-controlled, randomized crossover study. And what they see is vitamin C supplementation was found to decrease the urinary concentration of lipid peroxidation metabolites by 20 to 30% in support of the notion that vitamin C supplementation exerts antioxidant effects and reduces oxidative stress in vivo. And we have a paper here, and what they show is you have lipid peroxidation occurring here. Vitamin C is basically preventing the reactive oxygen species or the free radical from interacting with the lipid. And then basically also vitamin E is managing the lipid peroxidation, the lipid peroxyl itself. The vitamin C is recycling the vitamin E. So basically vitamin C is working to directly manage the free radicals while also recycling vitamin E to protect against the lipid peroxidation here. Next up, in conjunction with vitamin E and vitamin C, you have glutathione. And the glutathione is a peptide composed of, as we can see here, glutamic acid, cysteine, and glycine. And its job is to help recycle vitamin C, vitamin E, and directly protect against free radicals and reactive oxygen species stress. And so inside this study titled Glycine and N-acetylcysteine, Supplementation in Older Adults Improves Glutathione Deficiency, Oxidative Stress, Mitochondrial Dysfunction, Inflammation, Insulin Resistance, Endothelial Dysfunction, Genotoxicity, Muscle Strength, and Cognition, results of a pilot clinical trial. The researchers gave people 100 milligrams per kilogram of glycine per day and 100 milligrams per kilogram of cysteine per day. And they did this for 24 weeks. And basically what they found, and we can see this here, we have the plasma T-bars and plasma F2 isoprostanes. These are lipid peroxidation products. And you can see week 0 in this column, week 12 in this column, and week 24 in this column. For T-bars, the older adults start at 22.7 micromoles per liter. By week 12, they're at 14. And then by week 24, they're at 5.7. So essentially, they're almost 4 times less lipid peroxidation products by week 24 with this supplementation. For the plasma isoprostanes, at the beginning, at baseline, they were 185 picograms per milliliter. By week 12, they were 64. And then by week 24, they were 47.8. So again, significant drop in lipid peroxidation products by week 24 with 100 milligrams per kilogram per day of glycine and 100 milligrams per kilogram per day of N-acetylcysteine. Again, that's to create glutathione. So you can combine glutathione, vitamin C, and vitamin E together to synergize and protect against lipid peroxidation. Then we also have CoQ10. And basically, we have another double-blind randomized clinical trial here. So basically what they say in a recent double-blind parallel group randomized clinical trial, daily supplementation with 1,200 milligrams of CoQ10 was proved safe and resulted in a reduction in plasma concentration of F2 isoprostane, a marker of lipid oxidation in patients undergoing maintenance hemodialysis. So in patients with kidney failure who are on hemodialysis, giving CoQ10 improved or minimized lipid peroxidation. And basically the way this works is CoQ10 improves mitochondrial function directly. So we have the mitochondria here. On this left side, what we see is complex 1 is interacting with CoQ10 to pass electrons to complex 3. And here you have complex 2 using CoQ10 to pass electrons to complex 3. And so basically this helps to make sure that the mitochondrial electron transport chain is functioning well because it's one of the major drivers of reactive oxygen species stress. And then down here, we can see inside the plasma membrane, the cell membrane, you can see that CoQ10 is protecting against lipid peroxidation by recycling ascorbic acid and also vitamin E. So basically, it has a variety of benefits, and it synergizes again with vitamin E and vitamin C, and then also with glutathione. The last ones here are plant polyphenol compounds. So you have grapeseed extract, you have cocoa polyphenols, and then you also have pomegranate juice. So for the cocoa polyphenols, the studies used about 22 grams of cocoa powder and or 16 grams of dark chocolate or 36 grams of cocoa powder. And they say studies on the effects of cocoa polyphenols have shown that consumption of cocoa decreases LDL oxidation, lipid peroxidation biomarkers such as F2-isoprostane among healthy subjects. Then with pomegranate juice, what we can see is that they say malonyl-dialdehyde, which is a marker of lipid oxidation, was reduced by 24.4%, and protein carbonyls, which are a marker of protein damage from reactive oxygen species stress, were reduced by 19.6% and 17.7% at time 2 and time 3, respectively, supporting the evidence that pomegranate juice consumption enhances the antioxidant status in humans by decreasing lipid peroxidation and protein oxidation. Moreover, glutathione levels were significantly increased at time 2, indicating that pomegranate juice consumption improves the antioxidant mechanisms in red blood cells by increasing glutathione levels. So basically, the pomegranate juice and also the cocoa polyphenols will synergize with the CoQ10, the glutathione, the vitamin C, and the vitamin E to protect you from excess lipid peroxidation reactive oxygen species, and grapeseed extract can also do that as well. They say here from a meta-analysis that grapeseed extract supplementation caused significant decrease in malonyl-dialdehyde, again, lipid peroxidation product, oxidized low-density lipoprotein, so oxidized LDL, and high-sensitivity C-reactive protein, and marginally significant increase in total antioxidant capacity. So essentially, the grapeseed extract increased antioxidant capacity, lowered the oxidation of LDL, and decreased malonyl-dialdehyde, while also lowering the inflammatory mediator or signaling compound, high-sensitivity C-reactive protein. So we've set up the diet at this point, right? You're 4 grams per 2,000 calories per day of omega-6 polyunsaturated fats. You're having some seafood in your diet, so your ratio of omega-6 to omega-3 is probably somewhere around 6 to 1 or 4 to 1 or something like this. You have vitamin E on board, you have vitamin C on board, you have adequate glycine intake, you have adequate cysteine intake, CoQ10, and you've incorporated some dark chocolate, some pomegranate juice, and maybe some grape juice or grapeseed extract into your diet. Well, what's the next thing to look at with the polyunsaturated fats? It's the inflammatory mediators, because the lipid oxidation is under control and the amount of these things coming in your diet are low. So you should be decreasing your tissue stores of these fats. So now you need to protect against the excessive amounts of pro-inflammatory mediators. And now the way to do this is to block those enzymes that we talked about that create them. So you have lipoxyoxygenase and you have cyclooxygenase. The C4 cytochrome P450 enzymes, you probably don't want to block all those because they have a variety of different beneficial effects outside of creating these components. But cyclooxygenase and lipoxyoxygenase are the enzymes to look to block if you're loaded up on polyunsaturated fats and dealing with high levels of inflammation. And there's 2 components that can block these enzymes. So NSAIDs, as we see here, but a lot of NSAIDs are problematic. So the major one that has the cardioprotective effects and whatnot is going to be aspirin. Again, I'm not recommending anybody take aspirin. All I'm saying is that aspirin theoretically is able to actually block the cyclooxygenase enzyme, which can minimize the production of these inflammatory mediators, the prostaglandins and the thromboxanes. And then the other product is Boswellia, blocks not cyclooxygenase, but lipoxyoxygenase to decrease the production of leukotrienes. So essentially, these components can help to minimize the production of the inflammatory mediators. And so we have a study here. It's titled Pro-Inflammatory and Pro-Resolving Lipid Mediators of Inflammation in HIV, Effects of Aspirin Intervention. And they say studies investigating the mechanism of aspirin in general population, where it's used to reduce cardiovascular risk, demonstrate that via the acetylation of cyclooxygenase, so that's that inflammatory enzyme we talked about, this potent anti-inflammatory drug not only reduces the production of classic eicosanoids, namely prostaglandin and thromboxane, it also upregulates the formation of epimeric forms of several specialized pro-resolving mediators, i.e. aspirin-triggered specialized pro-resolving mediators. So aspirin triggers these pro-resolving mediators that help to actually resolve inflammation effectively. They say aspirin-triggered specialized pro-resolving mediators are linked with the regulation of both immune and vascular response to limit the onset and progression of cardiovascular disease in a range of experimental settings, including sickle cell disease, atherosclerosis, and neonatal hyperplasia. So essentially what you're seeing is aspirin blocks the production of pro-inflammatory mediators and shifts towards the production of pro-resolving anti-inflammatory mediators, which again is helping to shift the balance on those problematic polyunsaturated fats and then the subsequent eicosanoids, inflammatory mediators that are produced. Next up, we have Boswellia. So basically there's a component in Boswellia. It's called 3-O-acetyl-11-keto-beta boswellic acid. It's abbreviated as AKBA. Is the most active component of Boswellia extract and has demonstrated to be a potent inhibitor of 5-lipoxyoxygenase, so LOX, the enzyme that I showed you in the graphic, which is a key enzyme in the biosynthesis of leukotrienes, from arachidonic acid in the cellular inflammatory cascade. So basically, Boswellia can block the lipoxygenase, while aspirin can block the cyclooxygenase and shift towards the production of those pro-resolving anti-inflammatory mediators. So these are components that may potentially protect against some of the inflammatory mediators produced from the polyunsaturated fats. So with this combination of components, you should be able to manage the negative effects of the polyunsaturated fats while your body is lowering the amounts that are in your stored tissues because you've adjusted your diet. Now, with that, if you would like to see how to actually change your diet or how I've changed my diet to keep my polyunsaturated fatty acids very low, I'd recommend you check out these two videos in the cards below.